Hello, can you hear me now? You might also be seeing me. Okay. Great, great, great. Okay. I will stop sharing the video. Great. Okay, great. Sorry for the delay. And thank you for all the quick bursts on the WeChat. And okay, finally we can start. And sorry for the delay. Hi everyone, this is Yingjun, and today we are going to give a lecture and also an art session on these algorithms, EM and LDA. First quick survey, is there anyone who have ever heard EM or LDA before? Raise your hand. Good, as I expected. Well, before that, we like to see where these two methods are from, or what is the big picture about the machine learning. And before that, this is a screenshot from a cheat sheet, and this gives you a very quick grasp on how the machine learning has been distributed. And this is a very tiny book or a cheat sheet. And we can see that there are different sections or the chapters for that. And we can, through that, we are not really looking to the book, but we are see how machine learning are really clustered or the segregated. The first part is supervised learning, which is you might be very familiar, like those regression or the classification problem. And then the second part is the unsupervised learning. And you all know, or I can give a quick quiz, like what's the difference between the supervised learning and unsupervised learning? Anyone know? Yeah, exactly. With the supervised learning, we do have those label data, and we have those labels. And for unsupervised learnings, we have no labels, and we're trying to find the patterns behind the data. And there seems to some questions. Screen too small to read. Can you? Sure. 1 second. Oh, I see. They should seeing the thing outlines. Is it better? Okay, cool. Yeah. There happens a problem with the online students because on my local computer is in the presenter mode, so they are seeing a smaller size, but not for you guys. And I just turned that on, and everyone's happy. Okay, cool. As I just started, in machine learning, there are supervised learning and unsupervised learning. And recently, start from the neural networks, the deep learning is really popular, and which is quite also different from the supervised learning and unsupervised learning. And this book called the cheat sheet, also some refreshers or some background on math or some other tip or important tips. And you can take a look at that, which is very good, I think. I think is, as you can see, the page is only around 20 pages, but very brief, very important. And you can do a checkbook to see how much you have already into the machine learning field. And if some of the field that you have never heard of, and that might be a good start for you to look deeper in the machine learning. Okay. And for today, this is just a hook. And today we are going to, like you can see, the 2.2.1 EM, which is the expectations maximizations, which is where today we are going to talk about. As you can see, today we are going to talk unsupervised learning. As the in-class students have already answered, for the unsupervised learning, we are actually talking about those unlabeled data. And for those unlabeled data, one most important features is that there's no labels, or another way, there's no patterns. And we are trying to find the patterns inside. And there should always be different hypotheses that there are patterns. And for example, you might be, is there anyone here sitting here? I've ever heard of the k-means or KNN before? Yeah, yeah. And that is one of the most popular way or the most popular unsupervised learning, and which suppose there are k clusters already. So that is the hypothesis or the hypothesis underlying for using the clusterings, right? And usually, and for the classroom problems, and when, for example, like KN or K-means, there should be different clusters, and there could be different models, and those models, each model has the parameters, and all the parameters of the models are unsure or uncertain. And one of the problems in the models or in the clustering problems, we are trying to solve or settle those parameters. Okay, for example, in these two pictures, on the left is just data, but there's supposed to be two clusters, and where are the center of the clusters? And on the right, similarly, how many clusters are there? And what are the center, what are the variation of the centers are one of the problems during or solving the problems, okay? And here, we raise another very important concept, which is latent variables. Here I give the definition of the latent variables. Latent variables are the hidden or unobserved data help to estimate the clusters. Thus could be described in different ways. And here, as you can see, these three pictures show three very important and or famous or popular models here. And anyone can recognize any one of them? Or to give a guess what they are talking about? Any try? Any guess? Okay.
Does that mean the later the value of the later factor is determined by the value of the former one?
Exactly. For the third one, we are talking about the third one on the right. I can explain in a very brief word, and you can guess what this model is named according to my description. Here, x is the observed value, observed x1, x2, x3 until xn. And however, they are just for observations. And the real data or the real variable is the z. They are the latent variables. And x1 through xn are just like throwing the dice, have no relation between each other. But the x1 is related or dependent to z1, and z1 has the relation between all the z series. And if you are familiar with this process, this is very famous, especially for today, this so-called the hidden Markov. Okay, and this process is so-called the hidden Markov process, and this chain is so-called the hidden Markov chain. And the reason we put it here is to give you a clear mind that x is the observed data, but the z are the latent variables, which is very important in analyzing things. Okay, and also, anyone knows the previous two names of the models? I think the second one should be the most easy one. We just mentioned that. Yes, KNN. And or the k-means, we just use the data and we do the clusterings and sampling the centers of that. Okay. And for the very first one is the maybe not that popular, but maybe the most fundamental in this using the latent variables is so-called we can see that there all the histograms are the datas and that we observe at the background. However, with the two curved, red and blue, they are the two really distributions. So this is actually a mixture or a combination of two normal distributions, right? So this of that. In the following slides, we are trying to using this as an example to talk about how to deal with those mixture cluster or mixture distributions and try to using the EM models to get that. And here, let's come to our first hero or the first main character, EM. What is EM? On the left, I give the definition. The EM, or the expectation maximizations, this is algorithm, is an iterative method that finds the MLE by enlarging the sample with unobserved latent data. And here I also, oops, sorry, 1 second, I'm trying to plug in the charger. And here we notice that there comes a important concept, which is MLE. Anyone know what this stands for? Anyone in the classroom? MLE? Exactly. MLE is short for maximum likelihood estimation. And this is using one of the methods that where actually the results we return is the result that after calculating the probability and which with the most likelihood or with the highest probability. So all the method 2 algorithm today that we are going to mention, EM and LDA, are two of the probability methods or the methods. And we are trying to calculate the probability and settle both the parameter and our best clustering. Okay. And for EM, you can have a clear mind. And now we are going to our EM. And EM is using the iterations and find the best MLE. And you can think of the k-means or the KNN to think about that. And maybe we can see the picture first. In this picture, this slide I'm showing to you to how to explain EM in figures. And this is a this is for uncommon and Gaussian mixture, but you can also see it in KNN or k-means as you are familiar. And for in the first picture or the first figure, all the gray dots are just the observed data, and there might be we can set with the very beginning we can see that or we can guess that there are 3 figures or the 3 clusters. And with these 3 clusters, by default, we usually seed first 3 original simple sets. And we calculate by the difference which or how all or each dots or the observations should be clustered in each clusterings. Okay? And so this is for the first step. And in the second step, we are calculating for all the points, and we send them all into their corresponding clusters as these figures show. Okay? And in the first figure, we get the parameters. We can see that the shallower one is the original parameter or the center in this case. And after calculation, we can see the real center or by calculation. This is the real parameters after this case. Okay, and after this step, and this step is so-called the E, expectation part, and this part is the M part. And after this, we are trying to go back using the new parameters or the new centers, and then trying to calculate again and to see how these dots or the samples are really splitted, and then go back to M again to calculate and to see refine the models of the parameters. And then we do a iteration or the circles for this, and after it converge, and we will see, so by converge, we can see that the 2 dots or the parameters that we estimated are the true results or the true parameters. They are almost the same, less than the threshold that we set. So we can see this is the convergence, and then this might be the final results. Okay, so this is the brief introduction on what is EM, and there seems some questions for the online students. Oh, no. And again, this slides talk about the how to explain the EM equations. And here we can see that on the left, still remember this is the combination of two Gaussian distributions. And as each per Gaussian distributions, we need to have the mean and the variations, right? And add the parameters. And as a combination, we can write the target form in the very end on the left bottom part. And this is our target functions. And here we are trying to calculate and by maximizing the likelihood of these functions and to try to see those two parameters. And here we are doing exactly the same thing as what we did in the last slides, but that is in figure. And here we are trying to do that in mathematics. See what I mean? And again, first of all, we are trying to see that for each distributions in this equation, we have the mu1, sigma 1, and mu2, sigma 2. And from the very beginning, we do the very default settings for each of them. And therefore, we have a very determined equation for this. And then we are testing for each of the all the data sets or all the examples and calculating the GM for the expectation for all of them. And after doing the sum or the integration, we can see that whether it's discrete or the continuous decisions, we can calculate either of them. And after that, we will try to use to do the M steps. We can try to maximum that and get the best parameters for those things. And with a refined theta or the parameters, we will go back to here and calculate again for that. And this is the same iteration and until it converges. Okay. So again, the very easy idea you understand this is just to take KNN or K-means in your mind and see how it goes the iterations. Okay, and the only things that you might not be familiar is how it goes to or turns to the mathematics functions or equations, and how to do the theta or the parameters refine, and that could be with the help of the software or with other mature software or functions. Okay. And before going to the LDA, any questions?
Then at the phase of convergence, I saw in the figure that some dots may be removed. Does that mean when we calculate, we remove some outliers?
That could be, but usually that does not happen that much. For example, in this case, now I'm trying to point to the two dots at I think the students in class can see this. There are two dots here. They are originally set to the blue, but finally they are just reclustered into different clusters. And we usually do not delete those dots, but I think you might be talking about those, right?
Actually, maybe it didn't delete, it just regrouping.
Exactly. And so that's what I'm talking about. We don't usually try to delete those dots, or all the data cleaning should be before this methods or before this process. But another thing that we can notice that even inside this, not all the data could be perfectly clustered. Sometimes it is because of the data quality. The final results could not be perfect. There should be some low precision or the low recalls that should happen, or that at least could happen. Okay. Okay, good. And now let's talk about the LDA. And yeah, someone told me that I need to do more R applications, so I will speed a little bit up. And here for LDA, we can see the figures on the bottom or at the corner. This is the main target that we are trying to get. LDA is a very famous method in the text mining. And in text mining, what we have is the first step, the documents. We usually have the corpus or a bag of documents. And in the documents, we can have those words, right? Each paper or each sentence have a lot of words. We have separate them those and get those terms or the words, they're the same. And using those terms or words, we are trying to find something that we are really interested, which is the topics. And here we can imagine that there's a hypothesis that the topics are really clusters of words. Can you see the connection? So that's why we are actually sending these methods under the EM or under the unsupervised learning. But the only difference is that we are no longer using the data, but using the text data. Okay. And here there are some hypotheses or the targets, basically what we did. And here there are some key assumptions saying that basically if we really want to using this, we can see that the LDA here actually you can see that is the latent Dirichlet allocation. And by latent, which means we are actually using the latent variables as we described before, which is the parameters of those topics or the parameters of those clusterings. And we set, using the EM method, we set the predefined one and try to refine those things in the EM processes. And here Dirichlet means in this text mining algorithm, we are assuming that those text words or terms are really in the Dirichlet distributions. And this is using the allocation methods or the algorithms trying to do so. So to generate a document, first of all, we choose randomly choose a distribution over topics and by those parameters. And then for each word in the document, we will try to randomly to see how they should be distributed in different topics, and then to refine the parameters. And after that, we will refine to the circle or iterations again and again as we previously described. And finally, we will talk about this using R algorithms. And this is in the very beginning paper, the data, the author describes here. On the left, we see that in the documents, there are different words, and some of them are very important as colored marked here. And on the right, it talks about how those colored words or terms are really helping to modify those topics. And in the middle, all the topics are final interests. Okay. And okay, and we are going to do the R implementation here. And are you all with me so far? Okay, and any questions? If no more questions, we are going to the R, and now you can open your R or R Studios. Okay, sure. I will do the R implication first, and if time allows, I will, in the very end, I will talk about the Dirichlet distributions. Okay. And if you are interested, you can download the R script through the GitHub, and I will show the GitHub. Here comes the repository for today's lab, and or you can just scan the try to find search engine tool and IS590DT and find today's lab, and there's R file and also the today's slides. And first of all, we are trying to download or using the data called here. I'm importing the JSS papers. I think that is the journal for scientific stats. And that is a journal mainly focused on the statistics and also some research on that. And here we are really talking about some really text data and in that journals. After installing the package, we can see the data here. And in this case, using R, we can see the dimension of the JSS paper is there are 556 papers, and for each paper there are 15 columns, and we can see what those columns are. Yeah, we can see that among those 15 columns, we have the title, the creator, the subject, distribution, and publisher, contributor, date, and so on. And we are actually basically using those abstracts and using those textual materials and trying to separate or split into different words or terms, and then try to make a prediction or the clusters using LDA methods. And again, here there are 15 column names, and we can see those. And these 5 are the package that we are going to implement or you need to install in before. And due to the time limit, I personally recommend you to listen to the lecture before and try to implement those on your local machine afterwards. Okay, and try to understand again. It's like what I mentioned in previous lectures. Again, the most important thing is not the software. It's not about how to run the software, but you can know what you can do with the software and how this could be implemented or applied through the R. Okay. And here we try to run the 2 libraries, TM and Snowball C. And the first thing, as you already know, we are trying to turn those 856 papers or 56 abstracts into a very determined matrix or data frame that in R. So this is the first steps. We are trying to process the data. And now we can see using after these few things, we are actually get the JSS DTM. DTM here is that I named it by the document term matrix. So after this, we can see that it is already 556 by more than 5,000. So here already each row it indicates a document or an abstract, and for each column is just a word or a term. And here we include more than 5,000 terms. Okay. And then here we can see what those words should look like. And I take the very first 20 words or the terms here, and we can see that they are ordered in an alphabetical way. And here, all those 20s are starting with the letter A. And here, I do a testing or a survey on the first column. Still remember, this matrix is about the documents and the terms. But in reality, for each document or for each abstract, it contains only a small fraction of all the 5,000 words, right? And for each column, which is for each word, it is not appearing in each document, and it only appears in very few documents. Are you with me? So that leaves that in this matrix, there are lots of zeros inside. The zero means the time this word appears in this document, the number or the occurrence is zero. And all these zeros happens a lot. Okay? And so this is a real question. And on the same time, we are actually trying to use those words or the words or as the features or the attributes, trying to predict those the abstract. So 5,000 is a little bit too much. So we are actually trying to do a brief feature selections or to cut down the number of those 5,000 words. And here I'm using a TF-IDF, which is one of the ways that we can trying to improve those the methods or to select the features. And has any of you ever heard of the TF-IDF method before? You do? Yep. For those who haven't, I also prepare slides here. TF-IDF, as I read on the left, TF-IDF is a way of the textual feature selection. We are trying to, again, we need to clarify the target. We are trying to find those important and useful words as our features, not just use any words. And what are the, or we can think that in this case, how we can think a term or a word is important. And in this case, there are two index or two directions we can think they are important. First of all, the term should happen frequently, okay? Because in this case, if a word only happens once, and that may not be a good indicator, okay? And should be at least some degree. And the second thing is that the word shouldn't be happen too many times. If just like the word and or comma, things like those, it happens almost in every document. It is not a good indicator as well. Okay, so we are actually trying to see on the second scenario, we are actually trying to see what is the frequency that each word happens in each document. The best part of the terms that we can imagine is that this word happens some of times, like tens of times, and it only happens in a few topics. For example, when I'm talking about like guns or the violence, they are only happens in a few abstracts or at least topics, right? And not like and or not like telescope or engine. They are too specific or too broad, okay? And we really want something in between. So there comes the two parts of the term frequency and inverse document frequency. The first term frequency here is how it's calculated. The term frequency is the number of times each term T appears in the documents. We will do the calculation. If that is too small, we will see it has a very low score. And the second part is that the inverse of document frequency. The document frequency, first, before inverse, we will see the document frequency is for each word, how many documents it contains those words. For example, I have 10 documents containing this word A, and this term frequency is 10. And then we will take the inverse, which is 1/10. Okay, we are trying to take that. In this case, we are really still think about the and example. We are not for and those appears a lot, and we by taking the inverse, the score is very low. See, and here, and after all, we will take the multiplications, or we times this both and have the final score at the TF-IDF. And sometimes it will have the 0 instead, and so we add 1 for each and take the log and add the final score. But basically, it's just the time for both parts. Okay. And in R, there's no mature TF-IDF, so we read those in person and trying to apply those things. You can see here, that I'm using the mouse or the pointer to apply is the TF LDF. The first part is we are trying to calculate the TF, term frequency, and we are not, because for each word here we're talking about the mean, because for each word the term frequency happens in each document. Like in document 1, there's a TF for the first word, for second word, right? For each of them. But we are only interested in the word, not really in the word in the document. So we take the calculation for each word and taking the mean of the average happen term frequency in all the documents. Okay. And the second part, we calculate the things that the documents and inverse the document frequency. After implementing that, we can see that the term we can see that for each word, there are more than 5,000 words. For each word, we'll get a score for them. Okay, and then we will trying to use the score to set a threshold and trying to see that, for example, in this case, I set the threshold to be 0.1, and we see that all the words or the terms that have the score lower than 0.1, we see that not that useful, so we just discard all them. Okay, and keep those things. So here we do the filtering. And now we can see how many still left. We can see here we only have that less than 200. And also we delete or discard those documents that not including those important words, because after deleting some words, there might be some of the papers or abstracts that we already found it useless or that not that technical. So we also take that out. So after this feature selection or the filtering, we found the data matrix is pretty much smaller than before, right? So with this, basically 200 by 200 things, and we talk about this. And then we can talk about the LDA methods. And here, as in EM or in the class rings, there has to be some parameters that you set before. And like KN, you have set how many clusters are there. And here is the pretty similar. Although we can do the EM, but we need to predefine how many topics that you are interested in. And here, this is the parameter that we are not really doing the iteration or will not change. Here we're doing the k equals 30. So it means no matter how the words are distributed, there should be returns through 30 topics, and we can see how that distributed. And we can see that here, LDA is already a built-in function or algorithm inside this. And we are using our data frame and using the K that we defined and using the method VEM. VEM is actually short for the variational, tab here, variational expectation maximize. So we can see that it is really just a variation of the EM and in the text mining methods. And then we get the LDA results, and we calculate the results, the probability, and the terms, and now we see that we add the topics. So here, we are only talking about that in these LDA methods, we can get those top 30 clusters and how words each terms really contributing to this. And we can see that here I really try to allow it to display the top 5 that with changing. We can also display the first 10 or the first 20 or first fields about that by changing the parameters here. And in this script, I also want to demonstrate a way which is word cloud to show your results. And we see that in each topic, there are some keywords. And for the distribution after calculating probability, different terms really have the different score or the different probability which it relates or which is dependent to the topic. So each term, so we can use the word cloud to show how that look like. And we can also show those figures here, implement all. And also can make a combination of the words. We can select the fourth, the sixth, the eighth, or some of the topic that we have listed and generate the word cloud them. Basically, like this. I change the parameter. You can make those figures or the word cloud much more beautiful. But this is basically this thing. Okay. This is our application part for the LDA or the EM, and the other because it's already implemented R, and you need to again to have a better understanding about the purpose of the document. Also understand you can the things and analyze the topics. Okay. And any questions? Any questions for the online students? And there are a few announcements that I need to clarify at the end of these things. It's like, first of all, thank you for all the feedbacks from the first lecture or the first lab last week. And after that, there's some response to your feedbacks or the feedbacks for your feedbacks. The first thing is that the time. And the time, this lab will not be held weekly, basically per weekly, per bi-weekly, or according to my announcement, or I will let you know for the notification on this lab. And for the time, most of the majority of the students think this is a good time, so we will basically follow this time. If it happens, it will be in Thursday. And also, I think students want me to emphasize more on how to implement those material or algorithm or models in R. So I think in the following weeks or the labs, at least 20 minutes, or for sure, we will trying to realize what we did in R and seeing that as a very important part. And also for the topics, I did list some topics in the repository, and you can trying to say that you can see about that, or if you find any interesting topics, you can feel free to email me and we can have it discussed. And also for the pace and background, we can see that actually last semester, according to the last week's the lab, someone says it's too mathematical, so we can notice that in this lecture, we're trying to avoid too technical. So we're trying to make it as clear as we can and let you understand in the first place. Okay, and if you're interested in the background, I do give you some reference, both videos and books and papers. And if you're interested, you can take a look at those references or come to me. We can discuss in person or after class. Okay. And for today's class, we do have a feedback in today's lab. And if you have time, you can check the last slides and go to this Google form and follow that. And there are just I think 2 questions or 3 questions. And if you have any questions or suggestions on both lecture part and the application part, feel free to let me know. Okay, and that's all for today. And thank you. And for online students, there any more questions? Bye-bye. And for Xinyu, and this recording will be closed, I think in 5 minutes. I don't know when it will be closed. So I think you have my WeChat, right? So you can talk with me through WeChat, and I can send you a paper on this, or we can meet in person on this distribution. Okay? Why is it the margin is too large? Oh, this is because the